Today we discuss section 2.5, the summary of row equivalence. So to start this section, we need to revise the equivalent matrices. Suppose we have a matrix 1, 2, 3, 4, and we know there are three elementary row operations are there. The first one is the interchange of two rows, say Ri and Rj in a matrix, and the second one is multiplying any row with the corresponding non-zero real number. So say C times Ri, and the last will be the Ri is changes to Ri times Ri plus some k times Rj, where k is a constant. So these are the three elementary row transformation. So first, if you write this is equal to or that is equivalent to, this is not equal to, equivalent to the matrix 3 4 1 2. Okay, so we can say that this is the equivalent matrix of this. Okay, we perform the first row transformation. R1 changes to R2. Okay, so R1 and R2 are interchanged. So what is the meaning of this? This is nothing but once you consider this these two matrices 1 2 3 4 and 3 4 1 2, can you make it an equality by using a matrix multiplied pre-multiplied from this 1 2 3 4? So that is obvious, that can be possible by choosing this matrix 0 1. When you multiply this matrix with this, you can get 0 1 times 1 3, that is 3 0 1 times 2 4, that is 4, and similarly 1 0 times 1 3 is 1, and 1 0 times 2 4 is 2. So this is because of this matrix. So this the action of this matrix on this matrix is nothing but the row transformation. So the first row transformation is nothing but a multiplication of this is true for any m by n matrix. If you consider some matrix like this 1 2 3 4 5 6, and it is equivalent to 4 5 6 1 2 3 by interchanging two rows. So you can make it equality by choosing a matrix. You can use the same matrix 0 1 and 1 0. Okay, so when you multiply this matrix with pre-multiply with this matrix, you can get this one. Okay, the action of this matrix is to interchange the rows of a matrix. Okay, now if you consider another row operation 1 2 3 4 is changed to some k times 1 and k times 2, that is 2k, that is 3 4. So can you make it equality by multiplying some matrix here? So that is also possible. That is because of this matrix k0 and 0 1. When you multiply this these two matrices, you can get first term as k, and second entry will be 2k. Similarly, the last row will be 3 4. So this is also true for any m-by-n matrix. You can use the same matrix to multiply a row with a constant. Similarly, if you write this 1 2 3 4 uh, as a matrix, I'll write it as some 1 times 3k, and 2 times 2 plus 1 plus 3k, and 2 plus 4k. And here we have 3 4. So I changed the first row as first row plus k times the second row. So can you make it equality? Yes, that is also possible. That is because of this matrix k1 0 1. Okay, sorry, this is not the matrix. Actually, that is 1 0 and 1k and 0 1. So this is that matrix. When you multiply it with this matrix, then 1 times 1 plus 3 times k, that will be the first entry. 1 times 2 plus 4 times k, that is the second entry, and the last row remains fixed, that is as 3 4. So these are how will you find these matrices? That is the idea here. So each row transformation is corresponds to a matrix multiplication or pre-multiplication by a matrix, a square matrix anyway. Even though this is not a square matrix, you can use this square matrix to obtain this matrix. So what is the idea of the row transformation? The idea of row transformation is each row transformation can be restated as a pre-multiplication of using some pre-multiplication using some elementary matrices. Okay, how will you get these matrices? That is the idea here. So in order to get these matrices, once you consider the identity matrix first. Okay, when you consider this identity matrix first, then perform the same operation what we have performed to get this matrix. Okay, in order to get this matrix, we need to interchange these two rows. Then by interchanging two rows of the identity matrix, you get 0 1 and 1 0. So this will be the required matrix for this row transformation. Then similarly, in order to get the matrix corresponding matrix of this row transformation, you need to perform the same row transformation on this identity matrix. When when you consider this identity matrix and perform this row transformation, C times Ri. In this case, that is K times the first row, so we can get the K times first row and the second row as it is. So similarly, you can perform this operation on or this operation on the identity matrix. You will get this matrix. Yeah, this is the idea of the equivalent matrices. So two matrices. So similarly, when you get two equivalent matrices, if you start with the matrix A and perform a row transformation, then you can get A1. Then again perform a row transformation to get A2. Similarly, etc. At last you get a B. Okay, then what is it? So we can say that A and B are equivalent matrices anyway. So how will you get this B from A? So in order to get this B A1 from A, you need to pre-multiply with the matrix P1. Say P1, that is P1 times A is equal to A1. Similarly, A2 can be obtained by pre-multiplying some matrix by matrix from matrix with this A1 and so on. Okay, so finally, in order to get the B, so we need to multiply with some P K times some matrix the previous matrix in the previous stage. So this from these two you can write it as A2 can be written as P2 times A1, and that A1 can be replaced by this, so that is P2 P1 A. Okay, similarly A3 can be written as P3 P2 P1 times A. Okay, so finally that B is the equivalent matrix corresponding to A. Then this B can be written as some Pk times Pk minus 1 times etc. P1 times A. Okay, or you can write it as some P times A. So these are the connection between two equivalent matrices. If A and B are equivalent, or this B is obtained by performing a number of row transformations from A, you can say that this B can be written as P times A. What is the advantage of this P, or what are the features of this P? This P should be this P is always a non-singular matrix anyway, because these are the product of such elementary matrices. These matrices are obtained by performing the same row transformations with identity matrix. So whenever the identity matrix is non-singular, then we can say that the corresponding row transformation never changes the singularity or a determinant of the changes of determinant, but the nature of the determinant. If determinant is non-zero, then equivalent matrix or this row transformation fixes that non-zero. If it is non-zero, then the equivalence matrix is also a non-singular matrix. So we can say that whenever this A is a matrix and B is the corresponding equivalent matrix, then we can connect these two with an invertible matrix P. Okay, that is the idea of a equivalent matrix. So in next section we will discuss what are the importance of these equivalent matrices. Now consider a matrix A. It's an m by n matrix, and this is belongs to F m by n. An m by n matrix is set of all m by n matrices denoted by F m by n if it is over F. F is a field. Now you consider this A as write it as A11, A12, etc. A1n, etc. AM1, AM2, etc. AMN. So this is our matrix A. This is n by n matrix anyway. Now you consider the first row alpha 1. Alpha 1 is nothing but A11, A12, etc. A1n. Okay, so obviously this is an element of f cross etc. cross f equal to f raised to n. That is an element of fn. Similarly, each alpha j is an element of this is n1 etc. n, an element of fn. Okay, now you can consider the rows of I call this as the rows of R1 and etc. Rn. Rn are the rows of the matrix A. So set of all rows of A, R1, R2, etc. Rn is a subset of Fn. Then if this is the subset of Fn, you can consider the span of this. The span of R1 etc. Rn, that is set of all linear combinations of these elements in these vectors in Fn. Okay, this is what we called the row space of the matrix A. Okay, so row space of a matrix A is always a subset of or subspace of Fn. Similarly, you can construct the column space using the columns of this, say C1, C2, etc. So those are the elements of Fm, okay, rather than this Fn. So now in this section we will consider, we will discuss the importance of the row space of a matrix. Okay, so once you write the row space of A and you consider another matrix B obtained by performing a number of row transformations on A, that means B is equivalent to A. Now you can get a non-singular matrix P to connect this A and B. Okay, then what are the relation between, our intention is to study the relation between the row space of A and row space of B. That means the row spaces of the two equivalent matrices. Okay, so once you have, this is an m by n matrix and this is our m by m matrix, then only this product will be defined. So then this will be m by n again. So what is the relation between these row spaces of these two matrices A and B? Okay, so we define the row space of A as this. Now you consider PA. What is PA? PA is obtained by this is P and this is our A. This is P11 etc. P1n, P1, P21 etc. P2n, Pn1 etc. Pnn. This is our matrix P and this is the A11 etc. A1n. Similarly, this is A1m, and I call this as a matrix of m by n. So this is Pm by m, Pmm. Similarly, this is m here. This is m1, and this is m1 etc. Amn. Okay, when you multiply this, let us take the very first row of this matrix. So what is the first row? The first row will be obtained by the first term will be obtained by multiplying this with the first row. Okay, first column, that is P11 A11 plus etc. P1 M AM1. This is the first entry of the first row, and what will be the last entry of the first row? That is obtained by multiplying this with the last column. So that is etc. etc. That is P11 A1M plus etc. P1M into AMN. This is the last entry. So these are the elements. Okay, now you consider this row as that is the first row of PA. I call it as the first row of B. So I put this row as B1. Okay, B1 is the first row. Then what is B1? The first row of B. Okay, that is nothing but this vector, right? That is p11 a11 plus etc plus p1m am1 is our p1m etc. This is the first entry, comma etc. Last entry is p11a1m plus etc plus p1m amn. So this is our b1, but this can be written as p11 times a11 a12 etc a1m plus p12 times a1 this is our a21 a22 etc a2m plus etc. The last we have p1m times am1 comma etc amn. Okay, when you add these all these vectors, you can get the first entry as p11 times a11 plus p12 times a21 plus etc p1m times am1. So that is the first entry of this vector. Similarly, the last entry will be obtained by, from this sum collecting the last term. So this shows that this is nothing but the first row of A, and this is the second row of A, and this is the last row of A. So we can say that the rows, this is last row, that is Rm. That means the first row of this matrix, the product matrix PA or the matrix B, is the linear combination of the rows of A, and similarly you can consider B2 and B3 and so on. So B1 is again a we can write it as uh, P, this is B1, so P1J, J varies from 1 to N, 1 to M, this is our RJ. Okay, so P11 here, then P12, P13 and so on. Similarly, this B2 can be written as sigma j equal to 1 to M P2J RJ, okay, and so on. So this shows that the linear, the row space of A is same as row space of otherwise the span of A, the span of the row space, the span of, we'll write it as span of R1 etc Rn. If we choose an element from this span, that element can be expressed as the span of B1, B2 etc. The rows of B. So the span of this vectors is contained in span of B1 etc Bn Bm. Okay, that is the we have M rows. So this shows that this is the row space of A and this is the row space of B. Okay, so row space of A is always contained in row space of B whenever we write this B is equal to PA. But we know that if A and B are equivalent matrices, this matrix P will be non-singular. Then you can write that A as P inverse into B, that is equal to some Q into B. From this you can conclude that the other inclusion, row space of B, is contained in row space of A. So whenever we assume A and B are equivalent, we can say that row space of A is same as the row space of B. Okay, these are the importance of the row spaces of two equivalent matrices. Whenever two matrices A and B are equivalent, then the corresponding row space will be equal. This is the next theorem.